Hey, what's going on, guys? I am back again with another video over exponential functions, growth and decay. All right, this is actually going to be day 2. All right, so it's 11.1, day 2. All right, and we are going to get started. All right, yesterday we learned about exponential growth and decay. All right, now we're going to talk about how you can model a growth or decay by a constant percent increase or decrease with the following formula. All right, this first part right here, here's our formula. All right, and here are your parts. All right, your final amount, your initial amount is A. All right, your time period is T, all right, and your rate is R. All right, it says in the formula, the base of the exponential expression 1 plus R is called the growth rate. All right, and the reason it's called the growth rate is because if it's 1 plus R, it is a growth rate. 1 plus R, please don't forget that. Growth rate is 1 plus R. All right, right there, growth rate, 1 plus R. All right, and then this other one is called your 1 minus R is called your decay rate. All right, now you think about growth is getting bigger, decay is getting smaller, okay? So we got some word problems right here. Remember this equation? All right, and let's dig in. On this first one right here, it says, Clara invested $5,000 in an account that pays 6.25% interest per year. All right, how much will she have in an account after 5 years? So let's label our parts. All right, what we got here is 5,000 is my initial investment. All right, that's why I initially put in here. So that's going to be A. All right, see your chart. 6.25 is your rate. All right, this is R. But remember, what you do with all rates, all percentages, you need to convert them to an actual decimal. All right, convert to a decimal. All right, so 6.25% as a decimal is going to be, remove the decimal twice. All right, so it's 0.0625. All right, that's my rate. And then per year, it says 5 years. So T is my time, okay? So now we have our equation. And what we do is we put it together like this. A, all right, little a, the initial rate times 1 plus. Because they tell us, right, and you think about the question, it's interest per year. She earns interest per year. All right, that pays interest per year, which means she's getting money. She's earning, it's a growth. All right, and then T is just 5, so that's our growth. And then you just plug it in just like that. All right, you just do 5,000 times 1 plus 0.0625, or you can do it that because 1 plus 0.0625 is 1.0625, excuse me. All right, and then you would just multiply, and that's how much she'd have in 5 years right there, okay? So $5,000 in an account that pays 6.25% of interest per year will have $6,770.41 in 5 years. All right, so let's try another one. It says in 1981, the Australian humpback whale population was 350 whales. All right, that's the initial, 1981. All right, it increased means growth, at a rate of 14%. All right, so that's R, but we must convert it. So 0.14 each year since then. All right, so it says write a function that models the growth. Well, first we got to make our function. So we have, and notice it didn't tell us a time. All right, it doesn't tell us how long. So right now it just says make a function. So we have A of T equals, or not, A of T equals the initial amount, 350. All right, times, this is a growth, 1 plus 0.14 raised to the T, which we can simplify to be 350, all right, times 1.14 to the T, okay? Now it says, what is the population after 5 years? Well, now we have a time. So X, or our T, is 5, all right? So we have 350 times 1.14, all right, like that. And when we get that, all right, it's going to give us, 1 second, it gives you 673.89. Now, when you think about this, you can't have 673.89 of a whale, right? What is it missing? A fin or something? I don't know, but we're gonna round it. All right, we're gonna round to the nearest whale. So we're gonna say about, all right, about or approximately 674 whales right there. All right, humpbacks. Okay. Now, right here it says Claire invests $5,000 to account that pays 6.25% interest. Wait a minute. Is that the same one? Yep, it's the same one. So I'm not even going to look at this one. Well, it's not the same one. This one says, all right, so let me restart. Claire invests $5,000 into an account, right? That's our initial, that pays 6.25 interest per year. After how many years will the investment be worth $10,000? All right, so this one's a little different. This one, we don't know how many years. This one, after how many years means T. We're looking for T. And our R, we need to convert 0.0625. We got to find T. We don't know. So doing so here, we make our equation. All right, like so. Same rules apply. +1 because it's a growth. And then what we're going to do is, all right, here's how you do it. You graph function y1, our function that we made, and then in line 2, we're going to put 10,000. And then you graph it, and then the appropriate domain you may need to adjust the window range. So we'll adjust the window range. I'm going to show you how to do that in a second. All right, and then it says use the graph to predict when the value of the investment will be 10,000. Find the intersection. All right, and on the graph per second, trace, intersect, enter, and you will get your value. Okay. So here's what you do. You go to your calculator, and for line one, we're going to graph the formula that we had, all right, or the equation that we made, which is 5,000 times 1.0625. And we're going to raise that to the power of x because we don't have a t, so we're going to raise it to x, okay? Then in line 2, we're going to do 10,000. And why 10,000? That's because that's what we're trying to see, when that function and when this intersects. All right. So now what we're going to do is hit enter, all right, or graph. And let me show you what happens. Let's spool in, let it spool. It's taking a long time. And then it finally stopped. So what I want you to do is this. All right, so you couldn't see anything, so what I want you to do is press window. Now, when you think about that 10,000, guys, that 10,000 is very far up the scale. All right, very far up the scale. All right. So what I'm going to do is, your calculator should already be preset for -10 and 10 right here. But that Y max, all right, that Y minimum, we're going to make 0, all right, because remember, the exponential function can't go past 0. But that max, all right, we're going to go up to 11,000, all right. We're going to go all the way up. Oh, that's 10,000. I'm about to type 10,000. We're going to go up to 11,000. Actually, you know what? I'm just going to do it like this. Let's go to 10,000 and 10,050. All right, just so I can have something beyond the 10,000 that I need. And now I'm going to hit graph. All right, and we're just looking for it to give us our value. So you'll see what I'm doing here in a second. Let it finish. There we go. Now I can see everything. Still. Oh, that's right. That's right. You see how this is up to 10? That's 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to go beyond 10 because that goes further than that. All right. So we're going to go. So back to window. I just press window. I'm going to make my X value a little bit bigger. All right, so let's say 50. All right, so let's see what I get. All right, yeah, we're definitely going to see the intersection now. All I do is make the X value larger, so now I have 50 numbers down here. Where'd that 10,000 go? Oh, there it goes. So there's my intersection. So now that I can see my intersection, I'm going to press second, trace. All right, then I want intersect, option 5. All right, and guys, look, this is going to take a lot of practice so you can learn how to manipulate the calculator. But anyway, first curve, and you just go enter 3 times. And there it goes right there. There's an intersection at 11.4. All right, 11.43. So back to our question. All right, I know we went through a lot right here. All right, we kind of got off track. You know what I'm saying? Trying to learn how to adjust a window. But It's for your benefit, okay? So now let's go back to the actual graph, all right? So you saw it say 11.43, all right? Well, that's what they got right here, 11.43 years, all right? So that's my X value that I saw on the graph was 11.43. So we would say that it takes 11.43 years for Clara to reach, for her investment of 5,000 at this interest rate to reach 10,000. So now here we go, man. Let's try. It says in 1981, Australian humpback whale population was 350. All right, and it increased at a rate of 14%. All right, remember, convert that to a decimal. And let me see, at a rate of 14% each year since then, use the graph to predict when the population will reach 20,000. All right, so we write our equation first. All right, we don't know what T is. All right, we're looking for T right here. It says when, so T. All right, question mark. We don't know what T is going to be there. Excuse me. But anyway, we go the initial amount, 350. All right, times 1 plus 0.14 raised to the T. And when we simplify that, we get 350 times 1.14 to the T. All right. So now we put that in Y1. And then in Y2, we're going to put 20,000. All right. So let's go back to the calculator. So I go back over here to the calculator. And our equation is 350 times 1.14 raised to the X. And then down here, we're looking at 20,000. So before I graph it, here's what I'm going to do. I'm going to go to my window. I don't mind about Y, all right, like negative 10 to 50, that's fine for right now. We'll adjust that as I go. But remember the number is 20,000. So I'm going to make this a little bit higher than 20,000. So 20,050 is cool. 20,100, something like that. All right, 20,000. That's 250, too many. 20,050. All right. Now I hit graph. All right, it should intersect somewhere in here. Oh, all right, there it goes. It's right at the top. All right, so anyway, let's see how many years it is. Remember, second, trace, intersect, enter. What's my X value? 30.888. So 30.88 years. So 30.88 years. So in 30 years, almost 31 years, the population will be 20,000 humpbacks, okay? Now, decay. Remember the formula for decay is going to be A, or here A of T equals A times 1 minus the rate to the power of T, all right? So city population, which has an initial of 15, that's our little a, 15,500 people, has been dropping 3% each year. So that's our R, which we convert to 0.03. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. So here we go. We have our equation. We're going to say 15,500. All right, and then we need to multiply by 1 minus the rate. All right, and when we simplify that, we get 15,500 times 0.97 raised to the T. So we're going to put that in Y1, and then in Y2, we're going to put 8,000, like that. All right, so back to the calculator I go. Let's clear it out. So 15,500 times 0.97 raised to the power of X. There we go. Make sure you raise it, guys, okay? And then we want 8,000. So this one, guys, we don't need the graph to go up as high. All right, 8,000. So I'm going to go and adjust the window, okay? Remember, the minimum. All right, the maximum, we don't need it to be way up here. So I'm going to lower it back down the Y maximum to about, let's say 9,000. All right, and then here we go. It's a decay, so it should come down this way this time. There we go. There we go. All right, so again, we're looking for the intersection. So second, trace, intersect, option 5, and then enter. Boom, 21.71 years. 21.71 years. So again, T equals 21.71 years, okay? Now, right here, we got this table. All right, there's a couple things I want to talk about with this table. Okay. It says the compounded interest formula. All right, that's the compounded interest formula. All right, again, with R, you're still going to convert R to a percentile. All right, and N is your number of times it compound. All right, so A is the amount earned. All right, that's the interest. P is the principal or your initial amount. All right, R is your annual interest rate. All right, that's your rate. T is your time in years, and N is the number of compounding per year. So let's talk about the number of times things compound. And you need to learn this chart. If something compounds annually, like you have an annual birthday, that only occurs once a year. Semi-annually will be twice a year. All right, twice a year. All right. Quarterly, think about a quarter. There's 4 quarters in a dollar. 4. All right, so quarterly is 4 times. Monthly is going to be, there's 12 months in a year. Weekly, there's 52 weeks in a year. And then daily, there's 365 days in a year, okay? So now, for this problem right here, it says you invest $500, that's my principal, into an account that pays 7% per year. That's our rate. So remember, we convert that to a decimal. Calculate when the amount you have, calculate the total amount you have after 8 years. Well, that is our time and principal. All right. So compounded annually. Compounded annually means N is going to be 1. All right. So I go back to my equation. All right. Remember the equation is A equals P times 1 plus R divided by N raised to the N times T. All right. So in this case, the equation would be 500 is my P times 1 plus 0.07, that's R, divided by N, once a year, compounds annually, raised to the 1 times 8, all right, N times T. And when I do that, it gives me $859.09. You can literally just put this in your calculator as is, which is what I did. I'll show you real quick. So you have 500, all right, times 1 plus 0.07 divided by 1 raised to the, all right, always put your exponent in parentheses. So it's going to be that's 1 times 8. You just put it in, all right, just like you wrote it, and then hit enter. There you go, $859.09. All right. All right, which is what we say we got. All right. Now, let's do another one. It says compounded monthly. So in this case, N is 12 months in a year. So that equation will be 500 times 1 plus our rate, 0.07, divided by 12, because it compounds 12 times a year. And then we're going to raise it to 12. Oops. There we go. 12 times 8. Again, put parentheses around this stuff in the exponent. So when you do that, you're going to get $873.91. All right. And then lastly, compound daily means 365 times a year. So when we plug that in, we have 500 times 1 plus 0.07 divided by 365, because we're going to compound more. 365. Ooh, that looks like 385. I don't want to confuse anybody. So divided by 365. Good night. I'm tripping. All right, raised to the 365 times 8. And again, put parentheses around your exponent so the calculator does it right for you. And when you do that, you get $875.29. Here, I'll write it up here, $875.29. Okay. Now, the last thing I want to point out is all your homework is right here. This video has reached its end, and I really hope it helps you prepare. I would watch these before I go to class and after if I need extra help. But anyway, man, that's it. Catch you later.